So my talk this morning is about why does yesterday's best practice become tomorrow's anti-pattern? You're all familiar, of course, with the idea of best practices, which is something that has proved consistently to work well on software projects. Many people misuse the word anti-pattern, though, because many people use the word anti-pattern as just something bad. But anti-pattern is a little more nuanced than that. It doesn't just mean something bad, because an anti-pattern, by the original definition, is something that initially looks like a good path and something that's a really good idea, but then eventually leads you to a really bad place. And so one of the things that I observed, and I'll talk about where this observation came from, was that yesterday's best practice very often becomes tomorrow's anti-pattern, and I got curious as to why is this true? And that's really what this keynote is about. But there are lots of examples of this, even right in front of you. Because when you look down at the keyboard that you use every single day, you know, the keyboard layout that you use is not the most efficient way to type. In fact, it was purposefully designed to be inefficient in a very specific way to make people alternate hands as much as possible. Because this is not how the keyboard started its life. The keyboard started its life, of course, as this mechanical thing that had arms that would fling up and hit a ribbon against a piece of paper. And the problem with this mechanical typewriter was that if you were a really fast typist and you got the keys too close together, the little arms would jam, and then you'd have to go and use some other ancient technology like whiteout or something like that to fix the problem that you've now accidentally created. And so when they created the QWERTY layout, they specifically designed it so that fast typists would alternate hands as much as possible. And there's an entire history of this on Wikipedia as to how QWERTY came about. And this is very much an example of a best practice because we had to design it for the mechanical constraints of a typewriter that has become an anti-pattern because it's not the most efficient way to type. In fact, Devoxx, of course, is a more efficient way to type, but if you want true torture in your life, learn how to type again. Start over with typing, and that's not a very fun thing to do. But then you'll also do some research and find out that you've been lied about QWERTY all this time, that maybe it didn't come from this alternating hands thing, that it was a shorthand created by telegraph operators. And of course, the truth, like many things in the real world, it's a combination of these things. Part of the design came from telegraph operators, but the real motivation was to keep the mechanics of the typewriter from breaking all the time. So this is an excellent example of yesterday's best practice becoming an anti-pattern. And very often these things have weird, unanticipated side effects. Like this, the missing 11th of the month. So this researcher got really interested in looking at the distribution of dates to see if more dates are in fact more important than other dates. And so what he did was scanned all the text he could find for hundreds of years of text looking for dates. And he discovered an interesting thing, that the 11th seems to be missing from history. Now, there are certainly some big events that happened on the 11th of a month, like September 11th in the U.S., and there have been some things that happened on the 11th. But on the whole, the 11th has sort of disappeared from history, and he got really curious as to why that is. Why is the 11th so missing in all of our history? Well, it turns out it goes right back to this, because you'll notice that this typewriter doesn't have a 1 key on it. Because when this typewriter came out, the lowercase l and the 1 were the exact same thing, and so the best practice on this typewriter was to use the lowercase l instead of a 1, and when you scan all those books in, it reads a whole lot of misspelled words of LLTH, which is the missing 11th of the month. And so just because of this weird design constraint on the typewriter led to all these other things, you end up with these weird rippling side effects like the missing 11th of the month. Now, you may have noticed, looking at my business card, that one of my titles within ThoughtWorks is Meme Wrangler. ThoughtWorks is one of those companies that allows you to choose your own title. And I chose this title of Meme Wrangler several years ago. Meme comes from Richard Dawkins. It's a viral unit of thought. Of course, you're familiar with internet memes, which are things that get really popular on the internet. And of course, wrangle is the English word that means to either herd or to settle disputes, like between arguments, and both those meanings work really nicely. But it's become sort of a self-fulfilling prophecy because I've started looking for trends and other sorts of patterns in the software world. And one of those memes that I wrangled not too long ago is the origin of the title for this talk, that yesterday's best practice is tomorrow's anti-pattern. And there are lots of examples of this in the technology world. Maybe the first best example of this comes from this famous paper from Dijkstra, where he suggested gently to an audience that maybe using GoTo everywhere wasn't the best possible way to program. And he almost got lynched very famously because everyone was very accustomed to the use of GoTo. And of course, he was saying use of GoTo considered harmful. But of course, now we know he was exactly right. But a great early example of something that was considered a best practice very quickly turning into an anti-pattern. You can see this in a lot of the technology world. If you look at all of the different patterns that Microsoft has done with their database access, they've used basically every combination of the letters D, O, and A except DOA, which is probably for the reason that that's a common acronym in the United States for dead on arrival, so they probably don't want to use data objects for access or something like that. But every time they come out with a new one, they tell you, oh, forget about the old one, that one's terrible, that's crap. You should go with the new one, it's really nice, but then a few years later they come out and say, oh no, you shouldn't do that anymore, that's a terrible idea, you shouldn't do that anymore. For a while they were pitching the idea that all business rules should be in stored procedures, and then a few years later they're saying, oh, you should never put all your business rules in stored procedures, that's a really bad idea, you shouldn't do that. In 2007 they came out with some new thing, and then they displaced that a year later, and now they're talking about some sort of cloud thing for their data access. Do I even need to mention Enterprise Java Beans as a perfect example of a best practice at one point becoming a giant anti-pattern because no one wants to really use this anymore? But this is a really interesting case. This really shows that names of things matter. Because Enterprise Java Beans in its later incarnations actually wasn't bad. The problem was with the name. So how many of you here have seen this movie, Plan 9 from Outer Space? This is probably a few hands here. You should go and seek this movie out because it is the worst movie ever made. It is famous for being the worst movie ever made. It is so terrible that it's great. It's so terrible it's actually moved over into the great category. This is the famous Ed Wood. But the problem with the worst movie ever made was, would you go see Plan 10 from Outer Space? And this is the problem that EJB ran into when EJB 3 came out, and it was not bad, but you're never going to go with something called Enterprise Java Beans after the first disastrous experience with it, and so names of things matter. Now, through the course of this talk, I'm going to be talking about various technologies, and some of them have not aged well, and I'm going to end up saying bad things about technologies and personifying technologies and saying bad things about them. And I was raised to never say bad things about people or technologies in public, but sometimes you have to do that for professional reasons. But I'm from the southern U.S., and fortunately, we have a great get-out-of-jail-free card anytime we need to say something really bad about something or someone. So if you say something really terrible about someone, like, that guy is as dumb as a bag of rocks, you can make that go away by tagging on to the end of it, bless his heart. So things I've actually heard my family members say, he's as dumb as a bag of rocks, bless his heart. Or he looks like he's been beaten nearly to death with an ugly stick, bless his heart. So you can say anything bad you want, just as long as you tag on bless his heart or bless its heart after the end of it. So it's a nice little get-out-of-jail-free card. And it turns out this is regional in the U.S., because if you're in New Jersey in the U.S. and you say something really terrible about somebody, you can make it go away by going, I'm just saying. So he's as dumb as a bag of hammers. I'm just saying. So that kind of mitigates that. And so anyone who would use Enterprise EJB3 is probably too stupid to write software, bless their hearts. So you see this yesterday's best practice becoming tomorrow's anti-pattern in the way that people use tools as well. And a really famous case of this happened back in the in the early 1990s. It was a really common practice in the 70s and 80s that projects would have developers work in isolation for long periods of time, and at the very end of the project, there'd be an integration phase. If you look at software engineering texts of the 70s and 80s, every project had this big integration phase at the end. And the idea was that all these developers work on all of their features in isolation from one another. And at the very end of the project, they all get those things together and integrate them all together to create some sort of release. And it turns out this is a pretty painful thing on a lot of projects. It turns out if you let developers, a whole team of developers work for months at a time and then try to integrate all that work, it's going to be a lot of work and it's going to be really painful. In the early 1990s, there were a group of developers who had collectively worked on a few hundred software projects. And they were frankly unimpressed with the way that people were traditionally, commonly building software in the early 90s. And so what they did was took a step back from all of the software development processes that were popular at the time and started just relying on their experience and took on this philosophy of we're going to take the things that we know have worked well in our experience on projects and just push them as far to the extreme as possible. These were, of course, the extreme programming guys. So they observed, for example, that on projects where we have lots of tests, it seems like we have better quality code, and so the most extreme version of that is to write tests before you even write code, which gives you the most extreme version of testing. They were also the ones that invented this idea of continuous integration because they observed that on projects where we were really eager to do integration, we had a lot fewer integration-based headaches than on projects where we spent a lot of time doing integration. And so this became one of the common practices in extreme programming and in fact in agile software development now, this idea of using a continuous integration rather than doing this big bang at the end. But there was an interesting side effect of this because when the XP guys started talking about doing continuous integration, people who were on traditional projects thought that was a terrible idea because they knew that the integration part of the project was the very worst part of the project. And if you force everybody to do that every day, that makes every day the worst day ever. Bless your heart. But then it turns out if you do it every day, it never grows into this monstrous big pile of pain. And so what the extreme programming guys kind of stumbled onto is this idea that's quite common in agile software development now, that when you find those painful little things like integration, you want to try to do those more often rather than less often, because if you can capture them really early, they don't grow into these big monsters of pain that you see before. So here's another little interesting best practice, anti-pattern kind of a thing. I want you to consider for a moment the Zen of the underscore on your computer. Think about what the underscore represents, because the underscore came about on computers like this. And on computers like this, and this is true for your computer as well, you can only put one character per cell in these computers. So, you know, the underscore wasn't designed as a way for developers to fake joining words together. It was really designed as kind of to highlight nothingness. It's very Zen, because you can't put anything else in the cell with the underscore except the underscore. All it does is highlight the nothingness that is above it. So it's a very interesting Zen-like key on your computer keyboard, because that's the only character you can put there. And what exactly are you underlining there? You're underlining space. Of course, that's not why it's on there. This is yet another example of a best practice turning into an anti-pattern. The only reason you have an underscore key on your computer keyboard is because the way you used to underscore things with one of these typewriters was to type what you wanted and then back it up manually and then underscore under what you had typed by typing over it, which is, of course, impossible on your computer screen. But now people are going to go away from this talk and say, yeah, it was supposed to be a talk about technology, but all he did was talk about manual typewriters. Bless his heart. So let's talk about the reasons that yesterday's best practice become tomorrow's anti-patterns, because that's what we really want to figure out, is why does this happen all the time? And I'm going to give you several of them. The first is increased tech stack complexity. So if you look at a common technology stack from 2005, it didn't have all that many moving parts. Now you can substitute technology names one for another, but none of the technology stacks were all that monstrously complex. Look at a common technology stack in 2016. Lots more moving parts. We have much more complicated architectures like microservices. We have big data, we have Kubernetes, we have data lakes, we have all these things. Our entire world has gotten significantly more complicated over time. And one of the problems as you get a more and more complicated technical stack is something that I call primordial abstraction ooze. Because every one of those little boxes there is really just an abstraction that you're representing around some tool or some framework that you're utilizing there. And not all abstractions are perfect. Many of them leak. This is the famous Joel Spolsky law of leaky abstractions. And so what happens as you make your technology stack more and more complicated is that little bitty leakages very low down in your tech stack tend to magnify as they go up into the tech stack and then manifest as this very, very unusual, very exotic error at the top of your world, and you have to now figure out exactly how all that happened through all of those fossilized layers of software. Another reason that best practices become anti-patterns is code reuse, or really code over reuse. Because one of the goals we'd really like to have is to write reusable code. And a lot of architectures were designed to help you write reusable code. But it turns out it's really hard to write reusable code. And very often, reusable code is not the same at all as code that you can just write once and kind of throw away. And this really came to the forefront quite recently with the 11 lines of code that broke the internet. You're, I'm sure, familiar with the leftpad.io phenomenon that happened about 6 months ago. If you're not in the JavaScript space, the brief story of this is what happened. These 11 lines of code was a transitive dependency on many of the major parts of the JavaScript ecosystem, like Node and several of the major pieces of that world. And the guy who wrote this had a little collection of utilities that he called KIK, K-I-K. Well, a commercial company came into the JavaScript space with the name KIK, and he didn't like that clash, and so he decided to take all of his toys and go home. And he removed leftpad.io, and for about 2 days, the entire internet around JavaScript was broken because nothing would build anymore because all the transitive dependencies broke. And in fact, here's a headline from the Register in the UK, how one developer just broke Node, Babel, and thousands of projects and 11 lines of JavaScript. No matter how many bad things you say about Maven, it never actually made headlines about how annoying it is. So this is pretty bad when you have developer tools making headlines in major papers. And this, it turns out, is one of our big headaches now, is transitive dependency management. And this is an interesting problem because this problem affects every one of our technology stacks. And there are not many problems that you can say affect pretty much every language and platform, but this problem does in fact affect pretty much every language and platform unless you've just built it very specifically not to do that. Here is a common transitive dependency management tree from the JavaScript world. Good luck figuring out what all this is doing in your project. And it is interesting how ubiquitous this is. So this is one of those problems I think we're going to have to solve. In fact, I think this is one of our 21st century big problems in software. One of my colleagues, Chris Ford, who's no relation to me, he lives in the UK, has said dependency management will be our go-to considered harmful moment. And I think he's probably right, because the first thing you can do to solve a problem like this is identify, hey, we've got this serious problem across all of our technology stacks. We need to start thinking about ways of fixing this, and I'll give you a few suggestions about that a little bit later on as I talk about remediation. One of the key reasons, though, that best practices from today turn into anti-patterns of tomorrow is what we're calling the dynamic equilibrium problem. Dynamic equilibrium, a lot of chemical systems are in dynamic equilibrium in that they've reached an equilibrium and then something comes into that equilibrium and it has to reach a new equilibrium. And the software development world is very much like that too, because you have the ecosystem that you can do things like planning against, for example, and then unexpected things will hit that ecosystem. A few years ago, a good example of this is when Docker hit the ecosystem. And as soon as it hits the ecosystem, it changes the ecosystem and everything has to now react to that new thing that has been created in that ecosystem. And so this is the problem of planning in software. Because if you're an enterprise architect and 2 years ago you made a 5-year plan and you didn't include Docker, as soon as Docker comes out, you can take that 5-year plan and wad it up and throw it away because it's now useless, because the thing you were planning against has shifted underneath you. And that's really tricky because you can build something that's perfectly okay right now, and then in 5 years it will suddenly not be okay when you haven't made a single change to it because the entire world has shifted underneath it in that time period. Here's a thought experiment for you. Take a computer, install an operating system on it, and some software like an application server and a bunch of libraries, etc., and then lock that computer into a closet for a year. Take that computer back out of the closet, plug it into the wall, plug it into the internet. What's the first thing that computer is going to want to do? 57 updates available. Even though you didn't touch a single byte on this computer, the entire universe shifted around it. Nothing in the software world is static. It's always shifting, and it's always in this dynamic equilibrium. And this is really tricky for planning because you can't really do long-term planning in software anymore because you can never tell when this dynamic equilibrium problem is going to pop up. So I'll talk about some solutions to that problem a little bit as well. Another problem we have that leads to best practices turning into anti-patterns is what I call the history problem. You're all familiar with this very famous quote by Santayana, "Those who do not remember the past are condemned to repeat it." This is particularly true in the software world because there's so many new things always coming at us. We very often ignore things in the past as being, how can that be interesting when there's so much new interesting stuff coming toward us? But this leads us into kind of bad places. There's another quote by one of my favorite American authors, William Faulkner: "The past is never dead. It's not even past. You think it's past and gone, but it's still in your face all the time, like the underscore key on your laptop." And a good example of this ignorance of history is this term that has become quite popular in this JavaScript world called transpiling. So this is what CoffeeScript does. When you produce JavaScript from some other language, you transpile it from some other language into JavaScript and then hand that to a JavaScript interpreter. I've got big problems with this transpiling term because all this really is code generation. But by inventing a brand new term for it, we actually do ourselves a big disservice. Because we've known about code generation for a really long time. The Pragmatic Programmer book has advice about code generation, that write code that writes code, that's a code generator, and don't use wizard code that you don't understand. So they understand both the uses of this and the bad uses for it and the places where you should be careful about using this. So that's the good thing about having a known good term like code generation, because we know where it works well, we know where there's some issues and challenges with it, and we know places you should never, ever use it. The problem with inventing a brand new term like transpiling is we have to learn all these lessons all over again for this brand new term, transpiling, bless our hearts. So it's crazy to invent brand new terms just so we have to learn brand new lessons all over again. We're much better off just calling it code generation, and with that term comes the good cases, the bad cases, and when you shouldn't use it. Remember, those who don't remember the past are condemned to repeat it, and so a lot of the JavaScript community is relearning the lessons we learned 3 decades ago. When code generators become really popular, we learn the good things and the bad things, and they're relearning those lessons one piece at a time. And then finally, best practices become anti-patterns because of sabotage, and sometimes willful sabotage on projects. Things like RDD, which is resume-driven development. I've seen several projects that were clearly the result of resume-driven development, where there'll be 4 or 5 web frameworks in the same project and an entire CMS copied and pasted into it. This is great if you're trying to make a really nice, fat resume, but terrible if you're trying to create any kind of maintainable code. Another common anti-pattern here are companies that do a lot of cowboy coding that really reward people who stay up late and really, fight and work 24 hours and really get stuff done at the last minute and can save the day at the very last minute by Herculean efforts of work. By rewarding people like that, all you're doing is making that more and more of a pattern, and you're going to rely on that more and more. And the problem is you're going to get closer and closer to the line of danger every time you do that until you finally fall over it. This is not good for sustainability in software for obvious reasons. Another version of inadvertent, accidental sabotage is highlighted by this example. So many of you remember the days when Internet Explorer dominated the browser market. And then the scrappy young upstart called Firefox came along. And Firefox was going to replace the domination of Internet Explorer. We're going to create a brand new open source browser, and we're looking for volunteers. And some of the things they needed for the new browser were things like the brand new Gecko rendering engine, which is going to be the brand new way they're going to render HTML. It's going to be so much better than the past. But they also needed really mundane things like a print preview dialog. So when Firefox went open source and they asked for volunteers, everybody and their brother volunteered to work on the Gecko rendering engine. And you know who volunteered for the print preview dialog? The underscore. Nobody did that because that's like your day job. Nobody wants to do a print preview dialog because that's the kind of stuff you have to do at your day job. Everybody wants to do exciting stuff. Nobody wants to do the boring stuff, bless your heart. But this is a problem that I've identified on projects all the time that I refer to as meta work is more interesting than work. Everybody in this room would rather build a framework than to actually use a framework to build something useful. That's meta work is more interesting than work. You'd much rather work on the build script than actually the thing that you're building. Very often you fall into this trap of meta work is more interesting than work because let's face it, many people in this room, myself included, that when you really boil your day job down to its simplest form, when you need to explain this to your grandparents, you say, well, I take things off web pages and put them in databases, and I take things from databases and put them on web pages. And that's not very exciting if you've done that for 20 or 30 or 40 different projects. So you know what developers do when their day job is boring? They invent cool puzzles to solve so that when they come into work, they've got cool puzzles to solve all over the place. That's meta work is more interesting than work, but this leads to a lot of very anti-patterny kind of behavior. Another thing that leads to a lot of bad things in the future is really strict governance. around teams and tools that they use, etc. And in fact, this is one of the big changes that you see in more modern architectures like microservice architectures. Because one of the tricky things when you're doing a monolithic governance is that you're doing all these things have to be shared together. They're all running in the same address space. They're all sharing all these, the same libraries, et cetera. Whereas in the microservice world, you're encouraged to run everything in their own separate process. So their own Docker container, their own instance of a virtual machine, et cetera. The real motivation for that is to not let every team pick their own technology stack just so that no other team can understand what they're doing. It's really about right-sizing technology choices for the size problem you have. Because one of the problems with really, really overbearing governance is that, let's say that you have a monolith and you have to choose something like an object relational mapper or a relational database. Because you're in a monolith, you have to make a decision that everybody can use. Now, if you're like most projects, probably 20% of your project really needs an industrial strength database, and the other 80% could get by with just simple data storage. But if you're forcing everyone to share everything, then everybody takes on the highest complexity for every project. And that's really the motivation in the microservices world of letting every team pick their own technology stack. It's not encouraging people to pick incompatible technology stacks. It's really about right-sizing the technology stack for the size problem that we have, because we've realized that not all problems of the same size require the same kind of technologies. And in fact, 20th century governance was very much about cost savings over guidance. A lot of governance in the 20th century was about cost savings and making homogeneous environments. But in the 21st century, that has very much shifted. It is much more about guidance now and a lot less about cost savings, which is a really good shift because we're not letting an external force like cost concerns overcomplicate our technology stacks. Another problem we realize is that some things just don't scale linearly. And what's tricky about this is that some things do. Your IDE, for example, is a good example of a tool that just scales forever because it works well with 100 lines of code and it works well with 1,000,000 lines of code. But some things don't scale linearly like that. Code bases don't scale linearly like that. Everybody here knows that a 1,000-line code base is profoundly less simple than a 1,000,000-line code base. Those things get way more complicated. And in fact, this goes back to the extreme programming story I told before and the origins of continuous integration. Because one of the things that they observed with continuous integration, but then applied this to a lot of other principles in software, was this observation. Now, what they were calling pain here is any sort of fiddly sort of work that you have to do that's kind of beside the work that you're trying to do, but necessary. So integration is one of those things. It's necessary, but it's not really the thrust. You don't come to work for the purposes of integration. You build a software project and you have to do integration as part of that. Setting up test data in a database so you can run tests is another good example of one of these little fiddly things that you have to do to actually get to your job. That's what they were identifying as pain. And you would think that as your project gets bigger linearly over time, that pain would get linearly worse over time. But it turns out this is not true. For a lot of things in software, pain doesn't get linearly worse. It gets exponentially worse. This is another one of those things that doesn't scale linearly. And everybody here knows what I'm talking about, because if you're using some sort of version control, like Subversion or Git, and you started working on a file, you know the longer you keep that out without checking it back in and reconciling it, the more likely you're going to get merge conflicts and other sorts of awful, nasty, painful stuff. So this ends up showing up in a whole bunch of interesting places in software. Teams also don't scale linearly, much to the dismay of many companies. An 8-person software project is very different from a 50 or 60-person software project, and it's really hard to make those really big projects work well. And in fact, what we've been seeing a lot out in the world is more and more realization that the way that we separate people has a lot to do with your human resources department or how you hire people, and not very much to do with building software effectively. Melvin Conway made an observation back in 1968, which has now come to be known as Conway's Law, which is that organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. Basically what he's saying here is that when you have groups of people communicating with one another and they're building stuff, their communication channels are going to end up being replicated in the stuff that they build. This is a really common thing. You hear this a lot in the microservices world. In fact, last year, O'Reilly, the publisher, did their very first software architecture conference in Boston. And I was on the program committee, so I got to see all the abstracts. And more than half of them were about microservices. And about half the talks ended up being about some aspect of microservices. But within the conference, it became almost an in-conference drinking game that every talk would eventually mention Conway's Law. So you waited for every talk to bring this up, because we're starting to realize how much impact team organization has on building effective architectures. And so what we're seeing a lot now, instead of using separating teams like this around their job title, is instead separate them by what they're building. This is a more domain-focused autonomous team. So these teams have developers and QA and operations and DBAs, basically every single role that's needed to solve that particular little domain problem is represented on this team. The goal here is to create a team where many of you at your day job want to do something, but you have to wait for somebody else. It's like, well, I really need to deploy this, but I have to wait for permissions on that server, so I have to wait for someone in operations. Or we need to do this, but we need to wait for changes that the DBAs have to make. The idea of creating these autonomous teams is get rid of all that artificial waiting, because every single role that needs to be on the team is on the team, and you can just get stuff done really, really quickly. We call this the inverse Conway maneuver. The realization is that Conway's Law is going to affect your team whether you want it to or not, and so you might as well embrace it rather than try to avoid it. And that's this idea of the inverse Conway maneuver. Now, if you're talking to an enterprise architect, they actually speak differently than other people, and so you might want to call this domain architecture isomorphism. It means the exact same thing, but anytime you're talking to an architect and you can get the word isomorphism in there, you get extra special bonus points. Another thing that doesn't scale linearly are tools over time. I mentioned your IDE. IDEs are good examples of tools that do, in fact, scale really surprisingly linearly well over time and can handle really enormously gigantic code bases sometimes. But other tools are not that good. So this is my former colleague, Kent Spillner. And in this picture, he's smiling, which is very characteristic of Ken because he's a very easygoing guy, very fun to be around. He jokes and laughs a lot, a very affable guy. But late one night in 2009, Kent wrote on his blog, "Maven builds are an infinite cycle of despair that will slowly drag you into the deepest, darkest pits of hell where Maven itself was forged." And I think it goes without saying, bless his heart. So why is he so passionate about a tool? Because this is just some build tool out in the world. What he's really touched on here is something I want to dig much deeper into, and it's these kinds of tools that I categorize as either composable or contextual. Composable tools are things like Bash and Z Shell, which are designed to take in raw text and produce raw text. And of course, by using pipes and filters and all those mechanisms and things like Bash and Z Shell, you can achieve some really amazing results. Things like PowerShell are more contextual, meaning that you still pipe things in PowerShell, but the thing you pipe on the other side is this thing that has properties and methods and that sort of stuff on it. So it's not just raw text, which is easier to use in a simple case, but you can't build as sophisticated things with it. Rake is a build tool in the Ruby world that's very composable because it's language-based. Ant and Maven are good examples of contextual tools. Because to make changes to Ant or Maven, you have to subclass from their API and bring in all that context before you can actually make changes to them. Emacs and VI are famously very composable because they're written in their own language. In the Emacs case, are written in a very low-level language like VI. Eclipse is very contextual because in Eclipse, you can make changes to the Eclipse IDE, but you have to understand the entire inheritance structure and how the interfaces work and how OSGI works and all that context. And so you could study Eclipse for a week to learn enough to bring up a new single window, whereas something like Emacs or VI is very simple, much more programmable. And in general, languages tend to be composable, and frameworks and libraries tend to be more contextual. So what does this mean? Well, more context means you get more out-of-the-box behavior, better contextual intelligence, like the case of PowerShell, where it knows what the values of properties are and types and things like that, but less ultimate flexibility and less power to evolve. In composable systems, you get less implicit behavior, but better building blocks and better eventual power, but steeper learning curves typically because you're after building smaller pieces together. Which all brings me around to this idea of Dietzler's law. So I used to work many years ago, before I joined ThoughtWorks, for a consulting company, and one of the things that this consulting company did was build projects for clients in Microsoft Access. And we eventually shut down the Microsoft Access part of our business and analyzed why we did that and codified that as Dietzler's law, which I talked about in my book, The Productive Programmer. And here's what Dietzler's law says. It's when you look at what your user wants, tools like Access make 80% of what they want super fast and easy. And this is true in every Access project. They all started out with stunning success because you could get so much done so quickly. The first 80% was really easy. The problem, though, is the next 10% is possible but difficult because now you're doing something the tool wasn't specifically designed to do, so you're having to kind of bend it or hack it or kind of go around or underneath something or kind of cheat a little bit and figure out a way to make that happen. But you can still figure it out, but it's difficult. But then ultimately the last 10% is impossible because you can't get far enough underneath the framework and the tooling and all that other stuff. And Dietzler's law says that users always want 100% of what they want and are never satisfied with less of that. And that's why every Access project ended as a failure, even though they started with great success, because we'd start out and give them a lot of what they wanted, then we reach a certain point where we couldn't deliver what they wanted anymore, and they were never happy with that. This is, in fact, what happened to all the 4GLs. Some of you may remember the late 1990s, there were lots and lots of fourth-generation languages around that were really popular. Paradox and DBase, FoxPro, which is still kind of around because every time they try to kill it, they won't let them. Power Builder was a really popular tool back in the day. But these are all gone now. Why did they all disappear? They all disappeared because they all ultimately suffered from Dietzler's law. And every single one of these tools you could get to sometimes 96% or 97% of what they wanted, but you could never get to 100%. And so that's why people always go back to general purpose languages to build stuff. And in fact, the thing that happened to the 4GLs is they converted themselves into domain-specific languages. That's what Rails and Gradle and tools like that are. They're fourth-generation languages written inside third-generation languages, which in many ways is better because when you reach that point where you can't get the framework to do what you want to do, you can dip down into the underlying third-generation language and actually make that happen. And so many of those fourth-generation languages, if we created them today, they would be domain-specific languages built on top of Groovy or Kotlin or Ruby or something like that. So what that means is that tool choices have life cycles. I'm not even suggesting that you don't use Maven. You should absolutely use Maven because it's awesome when you first start using it. But the thing about Maven is it's really opinionated and it's very rigid and it's very generic, which is great when you start a project because a brand new projects are really generic and you don't have a lot of opinions about how things should go. So it's okay to take its opinions about things, but then over time that gets worse and worse and leads you to kind of a bad place. So you have to watch out for tools like that. Don't not use Maven, but keep a close eye on it, because when you're using a tool like Maven, there will come a day when all the benefits start becoming disadvantages and you start fighting it. And once you start fighting it, it'll never really be happy again. And so you need to find something to move to at that point. But that's a really tough thing, because one of those anti-patterns is this idea of the sunk cost fallacy, that we hate to invest time in stuff and then seem like throw that time away to reinvest it in something else, but sometimes that's the smarter thing to do. Rich Hickey, who's the creator of Clojure, is also really quotable and has a lot of really smart things to say about software developers. And one of the things he says is that programmers know the benefits of everything and the trade-offs of nothing. This is one of the great things about being a developer, is you don't have to worry that much about trade-offs. That's the architect's problem, to worry about the trade-offs. Developers can just worry about the benefits and the cool stuff. Architects also have to worry about the trade-offs. And in fact, he has a fantastic keynote that he did at a conference years ago called Simple Made Easy, where he really talks about the difference between simple things versus easy things. For example, Eclipse is easy, but it's not simple. Emacs is simple, but it's not easy. And so there's an interesting difference between simple and easy. And that goes back to this idea of composable versus contextual tools, because as I said, Emacs is simple and Eclipse is easy, but that has interesting implications. And it also has interesting implications for us around things like libraries and frameworks, because libraries tend to be composable, meaning that you generally just dig into those and call the functions and things that you want out of them, whereas frameworks are typically things that you extend from and you write code inside that framework, and so those are a lot more contextual because you're inheriting a lot more context from that framework. Now, many of you are familiar with the ThoughtWorks Technology Radar, which is this white paper that we produce twice a year about our opinions about what's interesting in the technology landscape. And one of the things that we said a few radars ago that confused a few people, we said prefer libraries over frameworks. And what we really meant by that was prefer things that you can call versus things that you have to extend from. So one of the common definitions of a library versus a framework is a library is something that you call, a framework calls your code. So you extend from a framework and it calls your code. But when we think about things like transitive dependency management, one of the reasons we said prefer libraries over frameworks is that when you think about doing updates for these things, because new versions come out all the time for tools and libraries, in general, we're kind of recommending now that for libraries you take a pull approach. So in other words, if a new version of your library comes out, don't necessarily go and update to that new version until you need that new functionality. But when the framework that you depend on updates itself, you should do a push and update yourself as quickly as possible. Because many of you know the particular pain of a best practice turning into an anti-pattern when you rely on some fundamental framework like Rails or Spring MVC or some tool like that, and you let it get 2 versions out of date, and it's really painful to get it back in sync with the real world. And so because you depend so much on frameworks, be much more aggressive about pulling in updates from frameworks. You can be a lot more casual about that with libraries because you're much less coupled to those libraries. So the name of my keynote is Why Does Yesterday's Best Practice Become Tomorrow's Anti-Pattern? But maybe it should have been how to avoid yesterday's best practice becoming tomorrow's anti-pattern, because that would actually probably be more useful. So let's talk about that. So in many ways, when you look at software architecture, we're always fighting the last battle. And so the absence of architecture is our friend, the big ball of mud architecture. This is an actual visualization from a code base that I captured on a project that I was working on, doing consulting on. See the little tiny pixel-sized dots on the perimeter? Those are classes, and the red lines are the connections between all those classes. And the more weight on the line, the more connections there are between those classes. Trying to make a change in this code base sucks. And anyone who has to do that, you always have to bless their heart after they work on this code base. And you build a couple of code bases like this, and you go, man, I'm never building another code base like that, because making changes in that code base sucks. And so you build a layered architecture, which is really nice and organized, the presentation layer, the business layer, the persistence layer, the database layer. And this is awesome, because now I can swap out my entire persistence layer anytime I need to. I have a question for you. How often do you swap out your entire persistence layer? Pretty much never. But where does the thing you work on every day live in this architecture, like customer or orders? Well, part of customers in the presentation layer, and parts in the business layer, and parts in the persistence layer, and part is in the database schema definitions. So from a domain standpoint, from a customer standpoint, this is just like the big ball of mud. Because when I need to make changes to customer, I've got to touch every layer. I'm still touching every part of my architecture. This sucks as bad as the big ball of mud did. And so what you're seeing now is a big push toward domain-centric architectures like microservices, where the domain is the primary thing and the layers are now inside the domain. So if you look at that picture I had before, the layered architecture with customer embedded inside it, what microservices has done is just turn that inside out, and now customer is the main thing, and now the layers, if they exist, are inside each of those domain-specific classes. And microservices is not the only one of these. Service-based architectures, which are a lot less strict about things like database granularity and things like that, are also very heavily domain-centric architectures. And we're seeing this is a really common shift in the way that people think about software, is they're starting to model things around domains rather than around layers. So what many people really mean when they say microservice is a service-based architecture with domain emphasis and a modern DevOps practices. Many people who say they're migrating to microservices will not actually ever get anywhere close to this ideal microservice architecture with all these highly isolated bounded contexts and these isolated databases. The problem, though, is that saying that you're using microservices is cool, because that's all the rage right now in the world. So I'm officially in this keynote giving you permission that when you build a service-based architecture with domain emphasis and modern DevOps practices, you can still call it microservices so you can sound cool. So you have my permission to do that. So even if you're not actually building microservices but building service-based, you can still call it microservices if you want. We're doing a lot more of these domain-centric architectures, and that has big impacts on things like teams. This is where the inverse Conway maneuver really comes in around team organization, how we think about teams, around how we do governance. Because when you build these domain-centric teams, now governance all of a sudden becomes guidance around what tool choices this team has chosen. And governance becomes around things like, let's make sure that integration is consistent across all these different platform stacks, and make sure that things like logging and monitoring and all those operational concerns work across all those different technology stacks. This changes the way you think about coupling at the architectural level. This also focuses on what the real unit of change is. And this is the real reason that people have been shifting to more domain-centric architectures, is this is the common unit of change. Because when you make changes to your code at work, you're making changes to customer. And you're going to make changes to the presentation layer and the business layer and the database schema. Why not organize your architecture around that so that your common unit of change is the thing that your team is working on, not forcing you to coordinate between these artificial layers that you've created for reasons that are now outdated and have become anti-patterns. Another really nice solution to a lot of this problem is immutability. Now, there's a lot of immutability supported in modern languages, particularly functional languages like Clojure and Scala, and of course the real granddaddy of the immutable languages, Haskell. But the experience that all these languages are having over the last few years seems to indicate that if you use immutability a lot, you tend to get a lot fewer kind of weird side effect incidental breakages. That leaning on mutability simplifies a lot of your code in a lot of interesting ways. So for example, even in Java, when you create immutable classes, they're automatically thread safe. Those are the entire class of bugs that go away if you're dealing with immutable things. And so so this may be one of the ways to get out of things becoming anti-pattern so fast, is to create a more immutable infrastructure. But we need to think about this beyond just languages as well. I think we really need to start thinking heavily about the idea of immutable transitive dependencies. Because one of the things that we really care about in the continuous delivery world is building on known good assets. But the problem with doing that is if somebody from out in the internet can take all their toys and go home and break all of your builds, that's no good. That's not building on known good, solid foundations. And so one of the suggestions, this is a small part of the continuous delivery book, but it was really about a different way of thinking about managing dependencies. Rather than the traditional mechanisms we've been using to handle this, we've been using tools like Maven and Ivy to be able to specify a static relationship between libraries. So I have a pricing engine that relies on these two versions of these tools. This is a static reference to these transitive dependencies. But there's another model that builds a different kind of mechanism, a fluid dependency. So here's what a fluid dependency looks like. So I'm now saying that this pricing engine had a fluid dependency on this framework. So that means that when this framework undergoes a change, we automatically try to incorporate that change using a deployment pipeline and automatic triggering mechanism, automatically try to incorporate that into my pricing engine. And if it's successful, then it raises its version number. But what happens if framework undergoes a change and for whatever reason pricing engine cannot take on that change? This is a new kind of dependency called a guarded dependency. And the idea here is that you try to automatically take on that dependency, and if it fails, you flag it as guarded, and that means a developer needs to come along and untangle this and figure out why is this not fluid anymore? Why is this causing a breakage somewhere? This is really the continuous delivery attitude about managing dependencies, is to pull them into your code base as aggressively as you possibly can. As soon as there's a change, pull them in, try to do builds to see if they work, and if they don't for some reason, flag them so a developer can come find them and fix whatever that problem is. And it may be that you just leave this guarded forever because you don't want it to automatically upgrade to the next version. But typically what you'll do is fix whatever the breakage was and switch this back to fluid based on that new dependency. I think one of the things we're going to have to start thinking about doing is managing our own dependencies internally as an immutable repository. It's quite easy now to have your own repository internally. We should start viewing that more as an immutable store. And instead of just letting the internet update that anytime it wants to, take pull requests from the internet to update your internal repository. Because if you were doing that in the JavaScript world, you would have solved the leftpad.io problem, because as soon as you try to do a pull request that removes the fundamental library, all of your builds are going to break, and you would reject that pull request, meaning that now you're not relying on things that might break you out in the world anymore. And if that weren't motivation enough, here is a link to a web page, a malicious module on NPM. One of the slick things that JavaScript modules can do on NPM is when they install themselves, they can run code on your machine. And this one particular module on NPM, as soon as you installed it, its preload hook did an rm -fr/. And if you were running as administrator, that means that now it's time to restore your hard drive because it has now deleted your root directory on your computer. So some malicious things can happen through things like transitive dependencies. We're going to have to start managing that a lot more intelligently. I think this is the first step toward managing transitive dependencies a lot more intelligently across all the platforms that we have. We're going to have to solve this problem or it's going to drive us crazy. So the next way that we're trying to attack this problem is that we've realized that predictability is dead in architecture. Because if the entire ecosystem that you base everything on could shift dramatically at any point in time, you can't possibly predict anything. And so the book I'm working on right now is actually about building evolutionary architectures. And I'm doing a talk about this tomorrow, but I'll give you just a little bit of a sneak peek of that because this is really the core of what we're thinking about from an architectural standpoint. So this is our definition of an evolutionary architecture. It supports incremental guided change as a first principle along multiple dimensions. And I want to talk about two aspects of this definition. I'll talk more about it tomorrow, but I want to talk about two aspects of this. And one of these is incremental change. And so the assumption here is that you have a modern architecture like microservices or service-based architecture. You have modern DevOps practices with really good agility around deployment pipelines, things like that. In this kind of world, components are deployed into a production ecosystem. But we don't automatically release features when we deploy components, because one of the things that we commonly do is decouple component deployment from feature release. Because what that allows us to do is deploy components and make sure they're operationally sound, that they monitor correctly, they log correctly, they don't blow up and use a lot of memory and resources and other stuff like that. At some point later, we can turn those features on using routing or feature toggles or something like that, which also allows us to run multiple versions of a service that have slight differences side by side. Because what is typical in this world is that applications consist of the routes between the services that a particular service chooses to implement. And this is the real secret to incremental change at the architectural level. So let's say that you run WidgetCo, which is a web catalog of widgets that you can buy. And you allow people to star rate widgets, and they can also star rate shipping methods and also sales reps. And so you have a star rating service running at WidgetCo. And one day, you come out with a better star rating service that allows you to do half-star ratings, and you put it live. But you don't force anyone to use it, you just make it available to anyone who wants it. Gradually, over time, these other services are going to want these new features, the better version of star ratings, and so they're going to start routing to this new service. And over time, more and more people are going to do that. One of the magic tricks that Netflix taught us about architectures like this is that in these architectures, you monitor not only the services, but also the routes between the services. And any service that's no longer being routed to gets automatically garbage collected out of your production ecosystem. But notice that's incremental change at the architectural level. If one of your goals is adaptability, then this is one of the building blocks of adaptability, is to be able to put brand new behavior live at the architectural level, not force anyone to use it, but make it available, gradually let people move to it, and then get rid of the stuff you don't need anymore. This is one of the core building blocks of being able to build really adaptive architectures, is the ability to do this level of incremental change at the architectural level. The other aspect of the evolutionary architecture definition I want to talk about is this guided part, and this idea of fitness functions. So we're talking about evolutionary architectures, which are architectures that can evolve. One of the things in evolutionary biology that they talk about is the fitness of an individual over time. Its fitness is its ability to put its genes into the next generation. But fitness functions for architecture are really about quality of service kind of attributes. So what we're trying to build here are architectures that can evolve in ways that we never would have imagined, because we're freeing up teams to do what they need to do to solve business problems. But we also don't want to break things. So we have service level agreements for things like page load times, or we have auditing requirements about security. And we want to make sure that as it evolves, it doesn't break those things. That's what these fitness functions are at the architectural level. You define architecture fitness functions as kind of guide rails so that your architecture can evolve in all sorts of interesting ways as long as they don't trip over one of these fitness functions. And these are things like metrics or tests, and I'll show some examples of these in my talk tomorrow on evolutionary architectures. Here's an example of a Kvyat graph or spider graph from one of our projects that has fitness functions on it. All of these ilities that you really care about. And in evolutionary architecture, these become fitness functions. These are things that you can write tests for to verify, does my architecture still do these things that I need it to do? Does it still fit these criteria? That's this idea of an evolutionary architecture. And really what we're trying to build is this idea of adaptability over predictability, and make adaptability an ility in architecture just like scalability and all the other ilities in architecture. So to conclude all this, I'm a consultant, so I get to see a lot of really interestingly broken things out in the world. But there's this phenomenon in the consulting world called the out-of-town consultant effect. And what that means is, if I rode on an airplane to get to a meeting, I automatically have more credibility than the people who rode in a car to get to the exact same meeting. Because I'm the out-of-town consultant, so obviously my transportation costs more, so therefore I must be more expert for whatever that reason is. But there is a seed of truth to this out-of-town consultant effect, because it's a way to look objectively at things that you can't see objectively anymore. So many of you are familiar with a story from the book The Pragmatic Programmer about boiling frogs. Allegedly, if you want to boil a frog, you can't just throw a frog in a pot of boiling water, because he'll jump out realizing he's being boiled, bless his heart. The way that you boil a frog, it turns out, is you put him in a pan of cold water and then turn the heat up, and he'll cook gradually without realizing that. It turns out that that's not true. Even though it was in the Pragmatic Programmer book, it turns out that frogs are not that stupid. But the company you work for is that stupid. Bless its heart. Because you'll end up in this boiling frog situation all the time. And this is the real value of the out-of-town consultant effect, is the out-of-town consultant comes in and says, you guys realize you're just about to boil, right? And it's like, oh yeah, wow, it's hot in here. We hadn't even realized that before. Look at things objectively. And so the best advice is be your own out-of-town consultant. Go and look at all the things that you have in your ecosystem with an objective eye. Forget about all the history that led you to those things. Look at them and go, is that really efficient? Is that really the best way should we be building software? And reevaluate those things just like you're an out-of-town consultant. The last piece of advice I will give you, Glenn Vandenberg's a fantastic architect, and there's a great video of him doing this keynote on software engineering, and he has a great quote, that bad developers will move heaven and earth to do the wrong thing. The amount of innovation that bad developers put into doing the worst thing is amazing. If they'd put that much innovation into doing the right thing, we'd have the best software ever. But the amount of innovation that bad developers put in is really amazing. They will move heaven and earth to do the wrong thing. So my best advice to you is don't put all your effort into doing the wrong thing. Try to find the right thing. Don't be a bad developer. Bless your heart. Thanks very much for coming. Hope you enjoyed it. Thanks very much. Thanks.